let's discuss some of the topics. So the first question is, derive the elbow from KL divergence between approximate posterior and true posterior. Show explicitly how maximizing elbow minimizes this divergence. So the answer of this question is, to derive the evidence lower bound from KL divergence, we start by considering the difference between the approximate posterior and the true posterior. The true posterior is given by the Bayes theorem, which expresses it in terms of the likelihood, the prior, and the evidence. The KL divergence measures how different the approximate posterior is from the true posterior. By rearranging the terms and simplifying, we can express KL divergence in a way that involves the log likelihood, the prior, and the approximate posterior. The elbow essentially the negative of this KL divergence. Maximizing the elbow corresponds to minimizing the KL divergence, as the KL divergence is always corresponds to minimizing the KL divergence. The KL divergence is always non-negative. Therefore, maximizing the elbow helps the approximate posterior close to true posterior, effectively improving the model's inference. So the second question is, derive and interpret analytical KL divergence between two multivariate Gaussian distributions. To derive the KL divergence between two multivariate Gaussian distributions, we begin by recalling the formula for the KL divergence between two distributions. For two distributions P of z and Q of z, the KL divergence measures how much Q of z derivates from P of z. In the case of two multivariate Gaussian distributions, the first is parameterized by its mean vector and covariance matrix, and the second by its mean vector and covariance matrix as well. When you compute the KL divergence between two multivariate Gaussians, you find it that it depends on the difference between the means, the determinant, and the inverse of covariance matrices, and the dimensionality of the distribution. The formula involves the term that account for how different that means are, how different the shapes of distributions are, and how the variance of each distribution impacts this difference. The result shows that KL divergence is non-negative and provides a measures of the differences in shape and location of the two distributions. The smaller KL divergence indicates that the two distributions are similar, while a larger value means they may differ significantly. This is crucial for understanding how well an approximation matches the true distribution in machine learning and statistics. So the third question is discussing the implications of the KL divergence in the elbow as a regularizer. What happens if it is omitted during training? The KL divergence term in the elbow acts as a regularizer by ensuring that the approximate posterior is close to the prior. It prevents the model from overfitting to the data by forcing the learned distribution to stay close to a predefined simpler distribution. This regularization helps maintain generalization in the model, avoiding overly complex posterior distributions that might lead to a poor performance of unseen data. If the KL divergence terms is omitted during training, the model might fit the data very well, but it could also learn a very complex posterior that deviates significantly from the prior. This could lead to a overfitting, where the model captures the noise and the spurious patterns in the data rather than generalizable trends. Essentially, omitting the KL divergence term removes the constraint that helps control the complexity of the learned posterior, which can hurt the model's ability to generalize new data. So the fourth question is, explain the mathematically and intuitively why GAN training can suffer from the model collapse. Propose solution and discuss their mathematical reasoning. So for the fourth question, the answer is, in GAN, Generative adversarial network. Mode collapse occurs when the generator produces a limited variety of outputs, essentially mapping multiple inputs to the same output, which means it's not capturing the full diversity of the data distribution. Mathematically, this happens because the generator minimizes the loss function by finding a few points where the discriminator is fooled, leading to a generator to focus on these areas and ignore the other modes of the real data distribution. Intuitively, the generator might find that producing a few similar output considering fools the discriminator and thus gets stuck into the local minimum. This problem this is a problem because a good generative model should capture the full range of data variability. To address mode collapse, one solution is to add term to the loss function that encourages the generator to explore the more of the data space. For instance, one common approach is to use feature matching or minimizing the Jensen-Shannon divergence instead of the original loss function. This method helps to ensure that the generator doesn't collapse to a few outputs but instead learns to produce diverse samples by better approximating the entire data distribution. Another solution involves using techniques like Wasserstein GANs, which modify the loss to provide smoother gradients and avoid mode collapse, promoting more stable training. And the final question is explain how VAE can suffer from posterior collapse, discuss mathematical and practical strategies, for example, KL-alanine, to address it. In variational autoencoders, that means VAE, posterior collapse occurs when the learned posterior distribution becomes overly simple, often collapsing to the prior distribution. This means that the model ignores the input data and learns a latent space that doesn't capture the meaningful information about the data, which results in the poor generative performance. Mathematically, this happens when the KL divergence term in the elbow becomes too dominant. If the weight of the tail term is too large, then it forces the approximate posterior to match the prior, causing the model to ignore the data. Essentially, the model learns that the easiest way to minimize the KL divergence is by publishing the posterior to prior, resulting